Hi, my name is Nayani Torres,
Hi, I'm Marquisha Randolph.
and today we're going to present the railgun experiment. So there are basic principles of a railgun. There are two important components which include electric currents and magnetic fields. Our first one is electricity. Electric currents create magnetic fields. What we call electricity is the effect of tiny things that carry electric charge. Electric charge comes in two forms, positive and negative. Opposites attract. Positive charges are attracted to negative charges, while negative charges are attracted to positive charges. Positive charges repel each other, positive charges, while negative charges repel the negative charges, and therefore acting like magnets.
The second basic principle is magnetism. Magnetic fields push on electric currents. If something makes a magnetic field, then that same thing will experience a force when placed in an external field. The third basic principle is the railgun, a device that is simple in design, consists of two parallel rails and a movable projectile. The electric current will go down one wire across the projectile and then back down the other rail. In between the two parallel rails, both of the magnetic fields due to the rails point in the same direction and therefore create a stronger magnetic field. The magnetic field that exerts current energy onto the projectile to propel it out of the railgun, and boom, a projectile. When large amounts of power are used, the railgun becomes a potent weapon, but the principles can be demonstrated safely by using a smaller amount of power. It is important to note that when a small amount of power is used, the rails can be reused many times. If larger amounts of power are used, the railgun can become a one-shot device, as the rails are destroyed in the process of the shooting gun due to the arching and flexing of the rails. For our project, we will present a simple demonstration of a railgun using a capacitors and magnetics, which is called a linear homopolar motor. Also, we will demonstrate an example involving an electromagnetic rail accelerator.
Hi, my name is Jessica Williams.
Hi, I'm Codi Carnegie, and we'll be explaining how a railgun works. This railgun operates by running a current through two parallel conducting rails that are connected by a movable conductor, oriented particular to the rails. The projectile is attached to the movable conductor. For this example, we'll assume that the railgun consists of two parallel rails of cross-sectional radius r of 5 centimeters, whose centers are separated by a distance d of 25 centimeters, and which have a length of 5 meters, and that the railgun accelerates the projectile to a kinetic energy of 32 megajoules. The projectile also functions as a movable conductor.
Okay, so to start this example, we'll be using two formulas. B would be the magnitude of the magnetic field. And F will be the magnetic force acting on the length. So B is equal to U naught, the current 2 pi, and the radius of the perpendicular distance. Okay, so first we take the derivative of the force, which is I dx B. We substitute the B for this formula right here, and we get the derivative of F is I dx U naught I over 2 pi x. To find the force, we take the integral with the limits from r to d minus r. R is the radius and d is distance. After we worked out these integrations, we got the first equation, which is u naught I squared over 2 pi natural log d minus r over r. Because the magnetic field from rail 2 is in the same direction as the magnetic field from rail 1, the force exerted by the magnetic field from rail 2 on the projectile is the same as that from rail 1. Therefore, we get our F total to be 2F and our kinetic to be F total times L.
So we have our kinetic energy here as F total L. And then we plugged in the values of 2FL, which is mu naught I squared 2 pi the ln of d minus r over r, and multiplied by L. We simplified this equation, which we have here, and then we solved for I. After doing so, we plugged in our values, and then we came up with a value of I being 339,728.7 amps, which we simplified to 3.4 mega amps.